more people may come in a few minutes, but I think we could go ahead and begin. It is my great pleasure to introduce you to Dr. Blake Eason. I think he likes to go by Eason, Hildreth, who's interviewing for our comparative oncology research position here. He's currently a research assistant professor in the Department of Biochemistry and Molecular Biology at Hollings Cancer Center in Charleston, South Carolina. And he has a very interesting background. He's a DVM, graduated from NC State. He did his internship at the University of Florida. He completed a surgery residency at The Ohio State University, where he also gained a Master of Sciences degree, as well as a PhD, all at the Ohio State University. And the title of his PhD thesis was the role of PTHRP in skeletal development and bone formation. It was co-mentored by Dr. Volso and Dr. Toribio. He subsequently became a postdoc research fellow in the Ostrowski laboratory, and his focus was on the role of macrophages and osteoclasts in breast cancer bone metastasis. And he also did work on transcriptional microRNA regulation and myeloid and osteoclast differentiation. And he's also, and I was very impressed, he just was successful in obtaining a KO1 award with an impact score of 10, which that deserves a big applause. And the title of his project for his K, which is actually new, started just in August. Macrophage and osteoclast specific targeting for the prevention and treatment of breast cancer bone metastasis. So we will hear about that more today. And so help me welcome Dr. Hildreth.
Thank you very much, everyone. I told Dr. Carlson this morning that the visit just ended with dinner last night with Dr. Chow and Dr. Wood, and breakfast this morning with Dr. Lawrence and Dr. Rogati. It was worth the trip. Fantastic greeting and response so far, so thank you. Many years ago, I applied here as a surgery resident, so it was good to meet with some familiar faces from many years ago when I was not as wise but had a little bit more hair. Thank you for coming. So the goal of the Ostrowski Lab for over the last 20 to 25 years is looking at transcriptional programs governing myeloid, and more specifically macrophage and osteoclast differentiation. And what I'm going to present today is work that's been going on over the last couple of years since I joined the lab as a postdoctoral fellow after completing my PhD. And this work has continued since we made the move to Charleston about a year and a half ago. And then it's going to shift gears about the last 15 slides about how using this, it can be a means, targeting these transcriptional programs could be a means to not only prevent but also treat breast cancer bone metastasis, and significant comparative advantage in treating of primary bone malignancies, of which there's no explanation needed in this audience about the comparative aspects of canine and pediatric osteosarcoma. So the goal of this outline today is, first of all, we're going to start about two transcription factors, PU1 and MITF, and how they co-regulate the entire osteoclast transcription factor network. And that's a manuscript we just got published in the New Nature Family Journal Bone Research in March. Next, we're going to talk about a novel transcription factor that's important in T-cell biology of an EMS. Many of you know Lori Glemcher's work at Dana-Farber of EMS Dermin in regulating T-cell biology. We've actually shown to be a novel co-partner in PU1 and MITF in regulating osteoclast differentiation. We actually got that accepted in the new Cell Journal iScience this week, so it says in review on the CV, but it actually was accepted this weekend. And lastly, we'll talk about an NF-kappa B-dependent microRNA miR-146A. Of course, many of you know that's important in inflammation, but it's an endogenous regulator of not only hematopoiesis, but also osteoclastogenesis. And as I said, the last bit, we'll talk about current and future research about targeting transcriptional programs in macrophages and osteoclasts to prevent and also treat breast cancer bone metastasis. And lastly, future focus areas, which will hinge largely on collaboration with many of you if I am coming here to University of Minnesota. So osteoclasts are cells of hematopoietic origin, and once pluripotent hematopoietic stem cells come into the myeloid lineage, after becoming circulating blood monocytes or tissue macrophages, these cells ultimately fuse to become these large multinucleated osteoclasts, which are the principal bone-resorbing cell of the body. And unfortunately, whenever you look up a cartoon of an osteoclast online, it always looks like a scrubbing bubble flying around the shower from the 1980s. So there you have it, which is very important. So multiple transcription factors regulate osteoclast differentiation at distinct steps. And upon CSF1 signaling through cell surface CSF1R, there's a massive upregulation of a transcription factor known as PU1. However, upon co-stimulation with both CSF1 and rank ligands, signaling through cell surface rank, there's a commitment to the osteoclast lineage. And these cells ultimately become these large multinucleated cells that can also resorb bone in this characteristic lavender or trap staining, which is characteristic of osteoclast differentiation. However, during that process, multiple transcription factors regulate this process. Of course, three we'll talk about today: NF-kappa B, MITF, and NF-ATC1. Of course, NF-ATC1 is known to be the terminal driver of osteoclast differentiation and function. So many, when going back to veterinary school, for many of you, or the histology textbooks, you'll see you see these large multinucleated osteoclasts, and they sit on these scallop surfaces resorbing bone. And what a lot of people don't realize is these large spindle-shaped cells and smaller shaped cells here are actually mesenchymal stem cells or mesenchymal progenitors, and also immune cells that secrete CSF1 and rank ligand and actually ultimately modulate osteoclast function in the bone microenvironment. So one of these transcription factors, MITF, which is kind of like what my mentor is known for the most, and one of his former postdocs is actually here as a faculty member, Kim Mansky, in the dental school. So tomorrow when I meet with her, it's going to be past and present, looking right at each other. Because a lot of her work started this foundation, 15 to 20 years ago, not to date anyone in their involvement in the lab. MITF has been known to interact with multiple cell type specific transcription factors to regulate self-differentiation and ultimately function. And we know in osteoclasts, they control the transcription of multiple genes such as TRAP, which gives that lavender color, and cathepsin K, which is a protease, and the calcitonin receptor. But interesting from a cancer point of view, because mast cell tumors don't occur in human medicine, because only a veterinarian would say human medicine. We know that MITF is known to be a key oncogene in the development of malignant melanoma, independent of species. So how does PU1 fit into this entire equation? So what we know is upon commitment to the lymphoid lineage, there's a moderate expression of PU1, and this moderate level of PU1 expression is sustained as they become B cells or antibody-producing cells. And after commitment, low to non-existent levels of PU1 is expressed upon T cell commitment and erythrocyte or circulating red blood cells. However, commitment to the myeloid lineage has a massive upregulation of PU1, and sustained high levels of PU1 drive this differentiation towards monocytes and macrophages over neutrophils. However, despite this knowledge, no investigations currently have defined the role of PU1 during the full course of osteoclastogenesis once there's commitment to the osteoclast lineage. So work from our lab over the last 15 to 20 years showed that PU1 and MITF not only physically but genetically interacted the proximal promoter regions of key osteoclast function genes. And as shown here, this is a luciferase reporter assay based on the TRAP promoter, and TRAP of course gives that lavender stain. You'll see a lot more of that as we go on. When both PU1 and MITF are present, there's a massive increase in luciferase activity, suggesting transcription has been initiated. However, when either one is present or you modify the DNA binding domains, there's a much less luciferase activity. So then we looked at, well, what happens when you stimulate these cells with CSF1? And what we found is in the presence of CSF1, we see that MITF and PU1 bind to the promoter regions of other function genes such as cathepsin K and ACP5, but are not present bound to any exonic regions upon stimulation with CSF1. So evidence therefore exists that PU1 and MITF interact and are essential for osteoclast differentiation and function. So our objectives were to define the full extent of these interactions and then ultimately determine the magnitude of the transcription factor network regulated by both during osteoclast differentiation. So we perform this using multiple lineage-specific Cres to delete PU1 during multiple phases of myeloid differentiation in the osteoclast. And then we hypothesize that they interact and work together to control osteoclast differentiation function by not only governing osteoclast function genes, but also governing other key osteoclastogenic transcription factors. And in the manuscript, there's 6 figures. I'm only going to show figures 2 through 5 for the premise of this talk today. So initially, we use a myeloid-specific inducible CSF1R or CSF1 tamoxifen inducible Cre. So by doing that, we would delete PU1 specifically in the myeloid precursor compartment. And why we use an inducible Cre is, Steve Teitelbaum in Washington about 20 years ago, there was a Nature paper that showed that if you delete PU1 in myeloid precursors, these mice don't live past birth. And so we use an inducible system to induce PU1 deletion in this compartment in the neonatal period. So what we found is after 3 days of tamoxifen induction in 5-day-old mice, at 8 days of age, we see there's a pretty visible increase in bone mass here in the distal femoral metaphysis. So just to orient everyone, that's the region just above the knee and the distal part of the femur. And micro-CT morphometric analysis showed that not only there's quantifiable increases in bone mass and trabecular thickness, or the thickness of the spongy bone here, but also a decrease in trabecular spacing. And this suggests that there was an osteoclast defect present. However, what's going on at the histologic level? So what we did is trap staining by hand. So this is not on an auto stainer. What we show is that after 3 days of tamoxifen induction, there's a significant decrease in these large multinucleated lavender stained cells, the amount of surface cover, the amount of trabecular surface covered by osteoclast, but also a trend towards a decrease in overall osteoclast number. So then we decided, well, what if we delete PU1 specifically in committed osteoclasts? So this is cells that are after CSF1 array ligand signaling. So we use a constitutive cathepsin K Cre, and that would only delete PU1 once there's been combined CSF1 array ligand signaling in committed osteoclasts. And as you can see here, in 4-week-old mice, these are age-matched males. At 4 weeks of age, we see there's a significant increase in bone density radiographically at the distal femoral metaphysis, but also the midshaft or diaphysis. But then we looked at 8-day-old mice, so we age-matched back to the inducible model of myeloid cells and saw a similar bone phenotype here. So, but ultimately, what's going on at the histologic level, and what we see is there's a even more marked decrease in not only the amount of surface covered by osteoclasts, but also a reduction in osteoclast number. And then when we grew myeloid precursor cells and stimulated with CSF1 array ligand, we see there's a significant reduction. We don't need stats to see there's a difference here in these large multinucleated cells grown in vitro for 5 days. So then we know that PU1's involved, but how is PU1 regulating these effects? So we use a lot of CHIP or chromatin immunoprecipitation high throughput sequencing. So we see where proteins are binding throughout the genome and could the binding have any physiologic relevance? Because sometimes they're binding, there's not necessarily an effect. So we did ChIP-seq for both PU1 and myeloid precursors and osteoclasts, and then we did the same thing with MITF. And then we looked at shared targets. So where's PU1 and MITF both binding throughout the genome of myeloid precursors and osteoclasts? And then we did RNA profiling in myeloid precursors and osteoclasts. And the reason we did that is we do a lot of this, what's called overlay. So we have all these binding sites throughout the genome of what's their physiologic significance. So we then look to see what genetic elements are they, or genes of interest are they binding around they could possibly be regulating. And what we found is PU1 bound to 77,000 sites in committed osteoclasts throughout the genome, and the majority of these were in non-coding regions such as intronic regions or distal intergenic regions. And when we looked at where PU1 was binding throughout the genome, there was a significant overlap or where there was an enrichment for acetylated H3K27, which is a marker of actor enhancer elements in the genome. And this was much greater than enrichment for trimethylated H3K4, which is a marker of proximal promoters. And this suggests that PU1 might have its regulatory role by binding to enhancer elements and not necessarily to proximal promoters. This is how many of you and I have been trained to how transcription factors regulate gene expression. So then we looked in the genes associated with these 77,000 binding sites and saw there was about a 90% overlap in PU1 targets in both myeloid precursors and osteoclasts, suggesting that PU1 might be poisoning the genome for differentiation even before there's rank ligand signaling. So then when we overlaid these PU1 binding sites with gene expression, we see that osteoclast differentiation is a significantly enriched biological process, and second of all, bone remodeling. So no bone remodeling, you need osteoclast activation before you have bone formation. So then when we took the original myeloid precursor model and we deleted PU1 specifically in myeloid precursors and grew these osteoclasts in vitro for 5 days in gene expression, we see there's a significant reduction in committed osteoclasts when PU1 is deleted of key osteoclast function genes. So we then went back and looked at, well, how's PU1 binding associated with these genes? And what we found was that binding at regulatory elements associated with these 3 osteoclast function genes of interest, while there was a significant increase or a trend towards an increase in their binding once there's commitment to the osteoclast lineage, which makes sense, there's a pretty significant occupancy of these at these genetic loci prior to commitment to the osteoclast lineage, suggesting that PU1's getting in place for osteoclast differentiation even prior to rank-ligand signaling. So then we decided, well, we repeated the whole thing, but we did MITF, and similarly we saw that the majority of binding sites are intronic or distal intergenic regions, and when we looked at where PU1 was bound throughout the genome and in both myeloid precursors and osteoclasts, we found that MITF binding sites were centered over these same regions. And then we looked at the amount of overlap peaks, so we knew there was 77,000 binding sites of PU1 and osteoclasts, and while this represented less than 5% of the sites, or around 5% bound by MITF, this represented greater than 90% of the sites bound by MITF. So there was about 4,100 peaks that were co-bound. And when we overlaid this 4,100 sites with global gene expression, we found that transcription was a significantly enriched process, which is very encouraging, and secondly, bone remodeling, suggesting that, once again, PU1 and MITF are setting themselves up prior to commitment to the osteoclast lineage. And then we looked at, while this is only representing 6, we looked at 18 key activators or enhancers. You can't really say promoters, but these are genes that drive osteoclast differentiation, and then 3 genes that repress osteoclast differentiation. And when you delete PU1 in myeloid precursors, there's a significant decrease in genes that drive osteoclast differentiation, and there's a significant upregulation in genes that repress osteoclast differentiation, suggesting that PU1 not only controls pro-osteoclastic transcription factors, but also negatively regulates repressors of osteoclast differentiation. So then we went back and did traditional CHIP, looking at these pro and anti-osteoclastogenic genes, and what we found, interestingly, while there was sustained occupancy of PU1 and MITF, in both myeloid precursors and osteoclasts in all of these genes, giving further credence that they're present and setting up the transcription factor network even prior to commitment to the osteoclast lineage. So a term I've mentioned to many of you today is a term called a super enhancer. We briefly talked about an enhancer element prior in the talk. So super enhancers are enhancer elements throughout the genome that are in extremely close proximity. And typically when there's a binding of a transcription factor to an enhancer element, there's a mild to moderate increase in transcription. However, when a transcription factor comes to a super enhancer element, there's a massive upregulation of transcription of genes of interest. And this topic has gained a lot of traction in cancer because super enhancers elements are actually present in front of oncogenes, namely MYC oncogene and osteosarcoma in man. And so these super enhancer elements can be markedly upstream of the gene of interest. They can be downstream, and through changes in chromatin conformation that they can bind to the super enhancer downstream and then loop back to dock with the promoter region to cause increase in transcription, or they can be just directly upstream, similar to what a promoter could do. So What we know is that superenhancer regions are marked within the genome with an unusually high level of binding of a protein called BET activator proteins. And these BET activator proteins are like an accessory proteins that drive transcription. And so, since BET proteins, namely BRD4, which is a lot of work done by a guy named J. Bradner at Harvard, who we've collaborated with, they're targetable. This is a way you can inhibit transcription of target genes by inhibiting BET proteins. So what we found is when we overlapped PU1 binding at noted genes important for osteoclast differentiation, namely NFATC1 and FOSL2, when we overlapped the PU1 ChIP-seq with publicly available BRD4 ChIP-seq from myeloid leukemia cells, so once again a myeloid population, we saw there's a significant overlap at regulatory elements associated with both with genes. And what we see is when we treat with a BRD4 inhibitor, namely JQ1 from Dr. Bradner, we inhibit BET. We see there's a significant reduction in the expression of these target genes, suggesting that BET inhibitors can actually inhibit target gene transcription and actually phenocopy PU1 deletion. But are PU1 and BET proteins related in any way? So this is my favorite part of the paper is this next slide. This is the best work, I think. What we found is when we took myeloid precursor cells and differentiated them into osteoclasts, and when you delete PU1, BRD4 binding is significantly decreased. So when PU1's gone, BRD4 doesn't bind to the enhancer, conserved intronic enhancer of NFATC1. So let's do the reverse experiment. So we actually then treated with JQ1, so BRD4 inhibitor, and when we do that, PU1 enrichment is significantly decreased. So if you delete or inhibit either one, the other is incapable of binding. So now we have a way that we can target a transcription factor, which transcription factors are largely known to be non-targetable. And so, in conclusion, we shown that PU1 is ultimately required for osteoclast differentiation and function. And that functional genomics revealed that PU1 and its co-partner MITF regulate a network of transcription factors, namely NFATC1, which is the terminal driver of osteoclast maturation, and that these transcription factors are also regulated by superenhancers, which bind or cooperatively bound by both PU1 and BRD4. And so we provide, in this manuscript, critical mechanistic insights into the regulation of a complex network governing osteoclast differentiation. So since this, we had some everyone has data left over. So in our looking for PU1 and MITF binding sites within the genome, we found there was a certain transcription factor called EMS, which showed a marked overlap in binding throughout the genome. So this is work we presented at ASBMR, or the Bone and Mineral Research Society in Montreal. It was a plenary poster and actually just got accepted this weekend in iScience. And I'm not underscoring the I at the front. We didn't get accepted in science. We got accepted in iScience. So I just wanted, the I is a normal case. So EMS was first identified to be essential for embryonic development, and has since been essential to shown to be essential for limb development, namely digit formation through regulating mesenchymal genes. It's been shown to be essential for development of the brain and postnatal neurogenesis. And as I showed before with Dr. Laurie Glimster's work, it's been essential for regulating T cell function. And we know that since then, SNPs and EMS have been associated with the development of rheumatoid arthritis, and SNPs have also been associated with the development of non-Hodgkin's lymphoma. So as I said, we found that EMS was significantly enriched at sites that were co-bound by PU1 and MITF. So we believe that EMS may be involved with these factors in regulating osteoclast differentiation. So going back, we use a myeloid-specific deletion model similar to the PU1, and when we delete EMS in myeloid precursors grown in vitro, we see there's a significant decrease in multiple pro-osteoclastogenic transcription factors and a mild but statistical trend towards an increase in transcriptional repressors. So what this suggests, based on just the repressor data and the genes that drive osteoclast differentiation, while EMS is important, it's not nearly as important as PU1 in governing osteoclast differentiation. So we then use traditional ChIP to see what was the EMS binding at the NFATC1 promoter, and what we found is while P1 binding is sustained in both myeloid precursors and osteoclasts, we see there's a statistical trend towards a decrease in occupancy once there's commitment of the osteoclast lineage. So ultimately what's happened, and we then did what's called chip-rechip. So we immunoprecipitated the chromatin with P1 antibody, and then we took the antibody off, and then we reprobed with P1, MITF, and EMS antibody. And what we found is that still there was significant enrichment of EMS and MITF and compared to input IgG at the conserved intronic enhancer of NFATC1. So ultimately what's happening in the mouse, because that's what in vivo is ultimately the phenotype you want to see, and what we did using the same myeloid-specific deletion model in tamoxifen induction, we see there's an increase in bone mass in the distal femoral metaphysis, and then we showed significant changes in morphometric parameters suggesting osteoclast dysfunction. When we then looked at trap staining once again, and we saw there's a significant decrease in not only the amount of bone covered by osteoclasts, but overall significant decrease in the number of osteoclasts sitting on the bone surface. So in conclusion, we found that EMS binds in a complex, and I didn't present that work. We actually used triple IP, we found using triple transfection, we actually found they all bind together in a complex at key osteoclastogenic loci in both myeloid precursors and osteoclasts. And that deletion of EMS, like deletion of P1, leads to decreased osteoclast differentiation and function. And so to date, we know that EMS has typically been associated with embryonic development and T cell function. However, to our date, you got to be careful saying this is the first evidence, because you might not know, so it's maybe out there somewhere. To the best of our knowledge, EMS has never been associated with myeloid differentiation, and what we've shown to be a novel regulator of osteoclast differentiation. So next we're going to shift gears quite a bit because we've been looking at transcriptional factors, but now we're going to look at one microRNA miR-146A, which is very important in inflammation, a kind of extension of David Baltimore's group, and that this is an NF-kappa B dependent microRNA. So NF-kappa B is essential for many inflammatory conditions, and also NF-kappa B is essential to drive osteoclastogenesis. And what we found is miR-146A not only regulates hematopoiesis as a process, but also regulates osteoclastogenesis. So this is a manuscript that's ongoing, and as always with mentors, not finished soon enough, you know, that kind of thing. So we know that miR-146A is a key regulator of inflammation, and it's induced by pro-inflammatory signaling cytokines through toll-like receptor signaling. And what's known as miR-146A is believed to be a physiologic braking mechanism on the immune system. So how this was discovered is patients with sepsis circulating values of miR-146A goes through the roof. And the reason it does is it's trying to dampen the immune system to try to prevent the immune response from ultimately killing the patient. So miR-146A polymorphisms have been associated with the development of certain cancers, depending on the patient population, such as thyroid cancer, gastric, prostate, and breast cancer, and also the development of autoimmunity. So SNPs and miR-146A has been associated with development of rheumatoid arthritis and the development of lupus. So based on the role as an inhibitor of inflammation, we believe that miR-146A could be an inhibitor of osteoclast differentiation, since osteoclasts are a very specialized myeloid phenotype. So what we found is using microRNA microarray, and I'm not going to say that 5 times fast, what we found in committed osteoclasts is a marked upregulation of miR-146A. It doesn't have the A here, but we're not looking at miR-146B. And in our time course experiment, where we differentiated osteoclasts and looked at miR-146A expression over time, we looked at day 3, which is a rather juvenile osteoclast. We see there's a marked upregulation of miR-146A within the osteoclast. So then we know that miR-146A is inducible by inflammation, so we stimulated both bone marrow-derived myeloid precursors and the RAW264 cell line with CSF1 and LPS, and we see there's a massive upregulation of miR-146A expression, but there's a lesser extent, but still increase when you stimulate with CSF1 and rank ligand or commit these cells to the osteoclast lineage. So for all the pathology people in the room, you don't like to see pretty pictures, and my mentor Tom Rosal would say, Easton, you didn't fill up the whole slide with one image, but just for time I have 6 images on one slide. What we did is looking at, we have 2 different mouse models, the miR-146A knockout mice, which we back-crossed 10 generations into block 6, and these are mice we got from David Baltimore, and then miR-146A knock-in mice, which express about 50 times the amount of miR-146A. as normal. We see that this phenotype here in the bone marrow and the metastasis region, this myelofibrosis that develops, is not new. David Baltimore's group has reported that, but however, they don't have access to the miR-146A knock-in mice we have, and what we see is there's a much different picture of cellularity, and also an increase in these large areas devoid of stain, which are lipid droplets within the, or adipocytes within the bone marrow, and also a dilation of the vascular sinusoids. However, when we take it to the diaphysis, it's pretty phenomenal phenotype that develops. Is once again, when you knock out miR-146A, there's a massive expansion in the myeloid compartment, this myelofibrosis. But in the diaphysis of the midshaft and the knock-in mice, we see these pink or eosinophilic staining regions here, and these shouldn't be there. These are retained trabeculae, and when the bone is growing from, these are 6.5-month-old mice, when bone's growing, the trabecular bone or spongy bone we see here should be resorbed as the bones elongate. And trabeculae should not be present within the midshaft of the diaphysis. So this is suggested to us that this retained trabecular regions of the diaphysis suggests that there's some type of an osteoclast defect in these mice, of which we know that mice with or anyone with osteopetrosis has retained trabeculae within the midshaft of the bone. So we did flow cytometry, and we did peripheral blood, spleen, bone marrow from a lot of mice, and we did a lot of different cell types. And what we found is that when we knock out miR-146A in green, we see that there's pretty much a global derangement, increase in T cells, decrease in B cells. But interestingly enough, there's a trend towards an increase of osteoclast precursors in the bone marrow and increase in osteoclast precursors in the spleen. But interestingly, there's a decrease in T regulatory cells, and this explains the phenotype of why individuals with SNPs and miR-146A develop autoimmune disease, since T regulatory cells help protect from the body from recognizing self. But interestingly enough, when we knock in miR-146A, we see that pretty much no cell compartment is touched except the myeloid compartment, when there's a significant decrease in osteoclast precursors in the bone marrow and the spleen. So in conclusion, we found that miR-146A, and there's more data to come, of course, in vitro and in vivo, I'm not showing, that miR-146A negatively regulates osteoclast differentiation, where our hypothesis was that it was a physiologic break, much like it is an inflammation, and that global deletion or overexpression results in cytologic changes, suggesting altered and extramedullary hematopoiesis. The spleens in these mice are about 7 or 8 times normal size in the knockout mice, and the knock-in mice, they actually have a mild increase in the spleen. I know there's a lot of work here in hemangiosarcoma. These knockout mice, when you age them past a year of age, they start to develop hematologic malignancies, both in the bone marrow and in the spleen and liver. And what we found is that effects are most profound in the myeloid populations, namely osteoclasts, and therefore miR-146A regulates not only hematopoiesis, which we knew from Dr. David Baltimore's group, but also it regulates osteoclast differentiation. So we're going to change gears for a little bit, and we're going to talk about what's going on now and what's going to go on at the next destination. Is that how looking at some of these transcriptional programs at the beginning about how targeting these can be a very specific way to target macrophages and osteoclasts. I'll talk about the more specific way in just a moment, not only prevention and treatment of breast cancer bone metastasis. So people say, well, how can you prevent bone metastasis? Well, I'm pretty humbled of the fact that the first graduate student my mentor, Tom Rosal, ever had was Lori McCauley. I don't know if any of you know Lori McCauley. She's the dean of the dental school at Michigan and one of the biggest bone researchers that's ever walked the planet. And her group's shown that calcium gradients, primary tumors release factors that cause bone turnover, release calcium, and those gradients then drive bone metastasis. And she's shown that pretty reproducibly in models of prostate cancer. And so in breast cancer patients that develop metastasis, about 75% of these individuals develop bone metastasis. And so cancer cells increase osteoclast activity, the bone resorption, and this ultimately leads to bone loss, pain, and ultimately pathologic fracture. So currently used drugs to either prevent or treat bone metastasis are aimed at inhibiting osteoclast function, and we know these are largely bisphosphonates and denosumab, which is an anti-RANK ligand therapy. However, the side effect profiles of some of these drugs are pretty significant, and it limits their use in some patients, particularly individuals that may have concurrent renal disease. So tumor-associated macrophages, or TAMs, are essential not only established in the pre-metastatic niche to primary tumors releasing soluble factors, but also propagating the growth of metastasis once they spread to bone. So a key axis of this is tumor-derived CSF1 signaling through cell surface CSF1R. So this is on great Dr. Lawrence is present today. Is this next thing is that CSF1R expression is restricted to cells of the myeloid lineage. So we've had a pretty fruitful collaboration over the last 20 to 25 years with David Hume. He used to be the director of the Roslin Institute at Edinburgh. He's kind of retired into a different scientific role back in his home of Australia now. So we've been working very closely for the, and I say we as a group. And so CSF1R expression is restricted to cells of the myeloid lineage, namely myeloid macrophages and osteoclasts. So CSF1R inhibitors gain a lot of traction, not only in lung and prostate tumors, but also in brain tumors by directly targeting tumor-associated macrophages. So our lab a couple of years ago had two publications that were very similar in regards to the outcome. Is that downstream of CSF1R is two very important ETS transcription factors, namely ETS2 and one you probably heard too much about today already, PU1. And so what we found is inhibiting CSF1R mimics ETS2 deletion in macrophages, and this decreases not only the number but overall size of lung metastasis following breast cancer metastasis. So in bone, tumor-derived CSF1 increases osteoclast activity, which requires PU1. And of course, we've seen what happens when you ablate PU1 in myeloid precursors, macrophages, or osteoclasts. So from this paper here in our research paper in Bone Research, I became interested in targeting the CSF1R PU1 axis in macrophages and osteoclasts as a means to prevent or treat breast cancer bone metastasis. So we know that genes regulated by super-enhancer elements are sensitive to BET inhibition, and we've shown this for PU1. So interestingly, BET inhibitors have been shown some efficacy in treating breast cancer, and these are agents that are these are entities that are chemo-resistant, and they may have additive or synergistic effects when combined with other chemotherapeutic agents. So literally, this was like a 5-minute addition before we submitted the grant. We have a bioinformatics guy in our group that came from us from OSU. I was like, tell me what you know about super-enhancer genes and osteoclasts and breast cancer. He went to his computer, messed on his keyboard just a little bit, and then 10 minutes later walked in and he said, P1 super-enhancer associated genes are increased in breast cancer bone metastasis in clinical patients, and they're negatively associated with survival. So this was a sentence we put in literally right before we submitted the grant the day of. So therefore, targeting BET proteins, namely BRD4, could be viable not only against bone metastasis, but also treating primary tumors and metastasis to other sites. So the next 2 slides is 5 years of proposed work in 2 slides, and I wish it was that simple to get a scientific accomplishment. So we don't use a lot of new mice now, we use syngenetic and immunocompetent models. So we're going to look at looking at two models of breast cancer bone metastasis, namely the 14-1 cells involved C mice, and we used doing an intratibial model of DB7 cells and FBN mice. And the goals of the award are to model distinct steps of breast cancer bone metastasis from orthotopic injection, so they have to get out of the primary tumor, go into circulation, then go to bone. Intracardiac injection, we have a good amount of experience with, where they just go into circulation to other sites. And lastly, looking at in-organ modification through an intratibial injection. So we're going to target the CSF1 axis by 2 ways. One is myeloid-specific deletion of PU1. So I've actually backcrossed our PU1 flux mice 10 generations into bulb C. So I did other work while I was doing that, but backcrossing 10 generations takes about 2 years to accomplish. So that's a very committed task. But I have a very unique mouse model now. And also using CSF1R inhibitors, which are in clinical trials at MUSC and also here at Masonic Cancer Center. So BET inhibitors, unfortunately, have a pretty global distribution once they get into circulation. So we're working with nanoparticle delivery people at MUSC to actually increase myeloid or macrophage and osteoclast specificity by liposome encapsulation. So macrophages and osteoclasts will readily engulf liposomes. So if you want to deplete either one in the body, load them up with bisphosphonates into liposomes and give it. David Hume's shown this, and you just obliterate all the macrophages and osteoclasts in the body, and then once the drug treatment stops, they'll rapidly repopulate. And we want to see is combination therapy therefore more effective. But so the goals are ultimately to constrain the microenvironment, not necessarily specific directly target the primary, the epithelial cells themselves. So we do a lot of bioluminescence imaging. A lot of that's my training from Tom Rosa about we use bioluminescence to monitor the development and progression of metastasis, and then use IHC, radiography, and advanced imaging to assess not only the primary tumors but also the metastasis. And then we want to see both in primary and metastatic tumor cells, macrophages, and osteoclasts, potential downstream targets of either pathway, and using chip RNA-seq. And at the end of this, we think we'll have a better grasp on the role that CSF1R, P1, and BET protein play in breast cancer bone metastasis. So three kind of, everyone's saying, well, what are you going to do next? Future directions. This is kind of like 3 slides, kind of like a pseudo chalk talk like kind of scenario. And so we know that targeting these different pathways will influence metastasis to or metastasis in other common sites of breast cancer metastasis, such as liver, lung, brains, and lymph node. So the beauty of using bioluminescence imaging is a non-invasive way. I mean, you could argue it's non-invasive, but you anesthetize animal, but it's a lot more forgiving than a lot more advanced imaging techniques that require radiation. We'll be able to track where the cells go if they go to other sites of bone. So we can also conduct histologic and molecular analysis on these sites that we identify and save upon mouse necropsy. And then from this, you can either initiate site-specific or multi-organ metastasis treatment, either after the development of or after creation, such as a direct inoculation of tumor cells, for example, into the liver. So number 2 is very interesting because I wrote this grant. I was sitting at Ohio State and I was writing this grant and I was like, oh yeah, we're going to go to Charleston. And it wasn't like a middle of the night decision, but it was like, I kind of wrote the grant there, and we got to see and have all the bells and whistles that we have at Ohio State. So actually, clinical trials are going on there and also here, evaluating CSF1R inhibitors and BET inhibitors as monotherapies for advanced breast cancer. So what does advanced breast cancer mean? Well, that's kind of the, some of these patients have bone metastasis, we'll have to find out. So there's a possibility that we can look at histologic and genetic changes in individuals from clinical trials here in the tumor cells, macrophages, and osteoclasts between primary and metastatic sites, and how they respond to CSF1R inhibition, BET inhibition, or response to other chemotherapeutics. So we've had a lot of experience. The lab's taking a huge shift towards pancreatic cancer now, away from breast cancer and macrophage and osteoclast differentiation. And we've got a lot of experience creating patient-derived xenografts from a very, you got to be in the right, I wore the surgeon hat for many years, and I know when it gets late in the day, you might forget about getting that sample for the person that wanted to have it or what have you. But, got the right individual, the right setting of somebody that wants to be involved in research, you can readily get tissue specimens, provide all the paperwork filled out correctly. It's the biggest. We lose about 80% of our PDXs from pancreatic cancer due to improper informed consent files. All people that wanted to donate tissues from their surgery, but just signed on the wrong line, dated it wrong, so it's unfortunate. So you can use these PDXs to look at only primary and metastatic sites, but also cancer progression, the genetics of the tumor, both in situ and in the mouse, and also response to treatment. So from this, we may be able to identify patients with solitary tumors and also metastasis, notably to bone, that may benefit from either CSF1R or BET inhibition that may not currently be on it. So the last is where this vet school really buys in. I mean, this future focus area is designed for an environment where there's a cancer center and a veterinary medical center. And that's why when this job posted, I just jumped all over the application. Is the earliest data on the effects of BET inhibitors came from mouse models of osteosarcoma. So these are BET inhibitors acting on the mesenchymal neoplastic cells themselves and using mouse models. And what this data showed is they were primarily targeting MYC oncogene. So this complemented the existing effects of the anti-cancer effects of BET inhibitors on osteosarcoma cell lines in vitro. So there's a logical extension towards constraining the microenvironment in this breast cancer metastasis idea about using these therapeutic agents in both primary tumor to target the primary tumor and also metastasis of canine osteosarcoma. So based on, I know that the correct title is not clinical trials officer, I learned that this morning. So based on the vast richness of resources here and the Cancer Center, the comparative and translational research and extension of these findings, particularly into patients, namely dogs, going into the future could be limitless. So everyone has a slide like this. There's too many people to thank who's been involved, namely my mentor Mike Ostrowski and our funding. But getting here yesterday, I was like, wow, you go up north and it's covered in snow. It kind of looks like you're landing on the moon sometimes. But Charleston's a very sunny and bright place, and it's a place of historic beauty, as you see here. But there's a lot of water, and there's a lot of water in Minnesota. But there's a lot of water here and beautiful beaches, which we just agreed instantaneously, yes, we'll go to Charleston, but we didn't really know what a great place we were going. And that's great when you have a little sporting breed like this guy who likes to get into the water all the time. Here's the Medical University of South Carolina. Here's the Hollings Cancer Center, which our lab is right here. And we've been waiting a year and a half to move up here. You know, if anyone's ever moved from a space to a renovated space, you know how that will go. But I thank you all for taking the time out of your day to come to the talk, and the reception has been fantastic. Last Wednesday morning I woke up and I couldn't speak. Could barely say a word, lost my voice, and I panicked. I was like, I gotta go to Minnesota in 5 days. And I was like, I gotta be able to talk. So the lab knew I would get nod yes or no, and I would rarely say a word, say my voice when it came back. So I'm glad to have been able to deliver the talk here for you all today. Thank you.
Any questions for Dr. Hildreth?
I have like 7.
I thought you might.
Well, there was a lot of talks compressed into one, but
No, go ahead.
I will
We're
defer.
expecting you, Jaime.
I will defer. Okay. So actually the first question that I have is really simple, which is I might have missed the characteristics of the model that you were testing for osteoclast development. It seems like everything was in vitro differentiation, and so is that correct? I mean, some of the stuff is in an animal model where you've done a genetic modification, but a lot of the getting from a precursor to an osteoclast is done
In vitro.
In vitro.
Yes.
And so one of the things that you mix, which is really interesting, is what happens to those cells as they interact with the microenvironment. So do you know when you modify PU1 or bed factors or MFAT-C1 or any of these other things, do the cells arrest but stay alive? Do they undergo like mitosis? What's the fate of those cells? And what do you think the fate of those cells would be in the live animal? And especially if it had a hypomorph rather than a complete knockout.
Yeah, so what I didn't show you is the inducible model. Of course, not all of our crees, despite when I came from a global overexpression or knockout model in my PhD. I just thought when you use Cree-mediated technology, it was gone, the gene of interest. So with the inducible system, we can probably get about a 50% knockdown in PU1 with 3 doses of tamoxifen. So we can somewhat titrate the amount of, and once we take the drug off, within 2 to 3 days, we can't tell the difference. So we can't titrate the dosage of PU1. In regards to the bone phenotype in vivo, I mean, it's real. We don't know, a lot of people say, well, when cells commit to the osteoclast lineage, do they then bind to other mononuclear osteoclasts to become the multinuclear, or are they binding to other macrophages? And no one knows that answer. It's much more economical to bind to a macrophage to form these multinucleated cells. So I think that, in regards to, we can somewhat titrate the dose there. We didn't do a dose escalation in vivo to see what's going on with the BET inhibitors. Now, the paper that came out in 2014 about mouse model of osteosarcoma and BET inhibitors, they thought they were targeting NF-ATC1. No, it's in Nature Communications, and it actually, we found that they were, but they were probably doing it through targeting PU1 first. So that's a very good question about the dose effects.
Because I mean, you've got sort of so many things happening at the same time, right? You've got lineage commitment, differentiation, homing, from the myeloid maturation compartment, perhaps even extramedullary, back to the osteoid compartment, and then fusion. And any one of those could get messed up, and I think the gross phenotype might be the same, but the consequences of mucking around with it might be really different. I'll just ask you one more question, because we'll meet tomorrow if we can discuss. So I was working with a company who shall remain unnamed, but they were one of the initial companies that had BET inhibitors. And they ultimately canceled the program because they could not overcome the toxicity of the BRD4 inhibitor. It was, in order to get into a therapeutic dose range, the side effects were unacceptable. So do you know if there are ways to mitigate that toxicity in patients?
Yeah, it's something that was a limitation. It's part of the reason we're talking about nanoparticle delivery. There's a lot of different ways. When I was an intern at Florida and they had limb-sparing dogs that came with osteosarcoma with infections, a research idea came from that localized injections, such as regional limb perfusion, could be a way. Direct inoculation into the tumor site could be a method. Nanoparticle delivery, there's been discussion of these RNA cages that can actually deliver as well. And also virus-mediated delivery into the microenvironment could also be a possible way. But I'm very aware, my mentor says Easton thinks about the animal first and the cell second. And he's like, I think about the cell first and the animal, so when we get together to talk, we think about these things. I'm very aware about the global effects that these drugs can have, but I know that by trying to minimize these off-target effects, we could have better therapeutic and more focused therapeutic efficacy. Thank you.
So I don't know if you could speak to the role of osteoclasts in liquid tumors, lymphomas, leukemias, and if there's a role for osteoclast differentiation, or at least osteoclast biology in setting up sort of a niche for whether it's lymphoma homing to a bone or leukemia viability in the bone marrow. I know that osteoblast plays a role in whether there's crosstalk between the osteoclast or osteoclast directly in terms of establishing and maintaining that sort of niche for those tumors.
It's very fascinating you ask that question, because there's someone that's actually here, a very recent appointment as the chairperson of biosciences, Kathleen Boris-Laurie. She was involved with the retrovirus PPG. My mentor was a part of it at OSU, and all they looked at was HTVL retrovirus-induced cancers, and namely lymphomas and leukemias in bone, and how they call us osteolytic lesions. So there was a lot of focus on that, and she's known a little bit about that, about how lymphoma can actually create primary bone tumors where there's not, there's recognized in people, there's primary lymphoma in bone, nowhere else. Can't find lymphoma anywhere else in the body, just in bone. So the same factors are involved, and I spent my, a lot of people, when I presented at a resident rounds, will talk about PTHRP as a bone forming effect. And Steve Berger, who trained me, was like, whoa, stop. PTHRP is a lytic factor. It causes high calcium in cancer patients. Well, lymphomas are known to produce a large amount of PTHRP that actually then act on osteoblasts and then acts on osteoclasts. So they can, it's a direct effect from cancer cell to the osteoclast, like I showed in the original cell about the immune cells releasing factors. But also, they can act through osteoblasts into there. So actually a lot of effects of PTH, as a bone forming, Lilly and excrete Forte and other drugs to treat osteoporosis. A lot of people thought PTH binds to osteoblasts and then there's a bone forming effect. Well, actually, if you ablate the PTHR receptor in T cells, there's no anabolic effect. So maybe T cells to begin with are the primary source of triggering bone turnover in the bone, and not necessarily osteoblasts themselves. Good. Thank you. So actually, BET inhibitors have gained a lot of traction for treating multiple myeloma.
Any other questions?
Thank you all for coming.
Thank you.
Thank you.
I know, and then,
Yes, absolutely. Thank you.
I keep complaining when I walk the dog.
Okay.
we don't have to go far. There was
Yeah.
That's
Just to update on Susan.
Yeah, just for a moment. Yeah.
She was your
I know where it is, right here.
full-time
Yeah.
volunteer, do one course at a time with the, whatever it's called, for the loves, you to pay for that. Just, oh, I have all the people there, she's coming. And I said, let me check and see if we need to modify the offer letter. You look at it too.
I saw your multiple
Our end, we
messages.
don't need to because
I will
more than
respond. Yeah.
nothing changes. And
Spending more
and
time
then she
evading
came back, I
messages
think
than
yesterday,
answering.
and I just.
That's okay, I figured you were, that's why I
All
was
day,
just
all
like,
day.
I'll just give it 24 hours and I'll
What about
ping
the
him again.
third technician
24 hours.
for neurology? And I don't remember anything about it. I think she said third.
We have lunch
An
out
additional
there, right?
technician.
Yeah, I think it's just right next door.
Because we're bringing them. So maybe that's what, I think I need to refer to David and
Sit there and be rude.
see, because I just don't remember
Yeah,
anything.
'cause I think, I mean, I don't see that neurology is technician-like, compared to some of the other
Well,
services.
she's not gonna come and do full-time
Right,
neurology either. And
right,
so
right.
I think if she wants something, we could say based on clinical load. But I think I need to touch base with Dave and see, because I'm not sure what to say about that. But maybe that's,
Okay, no, I'll just.
those are my conversations with her.
I will do anything that will get her.
That's how I feel too.
I think your conversation is getting captured on camera, just so that you guys know.
I hope that's not true.
You might ask Jessica to, because
It's
Yeah.
running?
I think it's running, so
Sure that-
make sure that it gets edited.
Yes.
Yep, you were on.
Yes.
Oh, no, okay.
So before it gets posted on the web, make sure it gets edited.
Thank you, Amy.
Yeah.
I'll tell Jessica.
Okay.
Okay.
Mrs. Like Smile, you are on.
Yeah, that's not.
So the other thing is that I had mentioned to her that,
Thank you for coming. I will see you at 7:15.
Yeah, well, I'm gonna have lunch.
Okay, great.